12.5 is your probability of independent and dependent events. Okay. What does it mean to be independent? On your own, right? By yourself. Okay, you can survive on your own. Okay, most of you, if you absolutely had to, at this stage of your life, should be able to be independent. Okay? If you had to be. Obviously, we don't want to be yet. Okay, and you don't have to be yet. Okay, but you're to the age in your life where if you absolutely had to be, you probably could be able to do it, right? Like, you know the essentials to life. Okay, you could be independent. Dependent means what? You need help. Okay, you rely on or depend on other people, right? So like a baby, dependent, right? They can't, young children, they can't do it on their own. Okay, they wouldn't be able to survive if they didn't have help. Okay, so that'd be like dependent. You're depending on something. Okay, so I'm not going to write the definition of independent and dependent because we kind of already know those. Now, the probability of independent events. Okay, so if I have two events, and they are independent, okay, meaning they are completely separate, right? They have nothing in common with each other. Okay, they have no reliance upon each other. Okay, so to find the probability of A and B, first of all, I know that the word and means to do what? Multiply. Okay, so I know I'm multiplying here. So if I want to find the probability that A and B both happen, I find the probability that A happens, and then I multiply it by the probability of B. And we've already kind of done some things like that. Okay, that would be if they were independent. Okay, so taking a look here at example 1, they tell us that you're playing a game that involves spinning the money wheel shown. During your turn, you get to spin the wheel twice. What's the probability that you get more than $500 on your first spin and then go bankrupt on your second? Well, does the first spin change what's going to happen on the second? No, absolutely not. It doesn't change your probability. Okay, so on the first spin, I want more than $500. So how many of those are more than $500? Are you just reading off of theirs? Yeah. But you could count if you had to, right? Okay. So the probability of spinning more than $500, okay, so the probability of A and B is 8 out of 24. And again, if you had to count those on your own, you could definitely do that. And means multiply times, what's the probability that I go bankrupt? Well, there's 2 bankrupts. They're both there in red. So it's 2 out of 24. Again, those are completely independent because the first spin has absolutely nothing to do with what I do on the second spin, right? Okay, so 8 times 2 is, or probably easier to reduce first actually, isn't it? Okay, 8 over 24 is 1/3 times 1/12. My probability is 1 out of 36. Okay, anybody have a calculator to give me that decimal? 0.0 what? 28, which would be 2.8%, right? Okay, so you have a 2.8% chance of that happening. What's that? Think so? Okay, example 2. Now, let's say you got 3 spins. What would you do? don't add it, but multiply, you just multiply another one, right? Okay, so let's take a look at, that's kind of what is happening on example 2. Okay, it says during the 1997 baseball season, the Florida Marlins won 5 out of 7 home games and 3 out of 7 away games versus the San Francisco Giants. During the 97 National League Division Series with the Giants, the Marlins played the first 2 games at home and the 3rd game away. The Marlins won all 3 games. Estimate the probability of this happening. Okay, well, the first 2 games were at home, right? What is the probability that they were going to win at home? 5 out of 7. Okay, that was the first game. Does that change the probability for the second game, though? No, it's still 5 out of 7, right? And then the 3rd game was away. What was their probability of winning in the away game? 3 out of 7. Okay, so what was the probability that they won all 3 games? Well, that's 25. Times 3 is 75. 7 times 7 is 49. 343, which as a decimal is, what is it? 0.219, which would be 21.9% chance, right? Okay. Could you have figured out on your own that those were independent events? Okay, that's the question you're going to have to ask yourself in today's lesson. Does this event matter when I think about the next one? Okay, does it have something to do with the next one? Okay, now let's take another look here at example 3. This is where it gets interesting because now you're throwing your permutations and combinations in. Everything's fine with probability until we start throwing those in, right? So far, everything's been good until we start doing our permutations and combinations. Okay, it says you collect hockey trading cards for one team. There are 25 different cards in a set, and you have all of them except for the starting goalie card. To try and get this card, you buy 8 packs of 5 cards each. All cards are in a pack are different, and each of the cards is equally likely to be given in a given pack. Find the probability that you will get at least one starting goalie card. Okay, so where are they getting their... So you can look down at the solution, right? Notice our question was, find the probability that you will get at least one starting goalie card. Okay, well, if you get at least one, okay, you might get 2, you might get 3, you might get 4, you might get 5. Okay, so your only one that you're not, only option of that doesn't work is not getting any, right? Okay, so what they're actually doing here, instead of finding the probability of getting one, they're finding the probability of not getting one, which is called the complement, right? Guys, remember we talked about the complement? We're doing the opposite, so we would actually subtract our probability. So where are they getting your 24 from? Right, that one card that's the goalie card. Okay, so they have 24. Why 5? Why did they choose 5? Because in each pack, there's 5 cards, right? And there's a total of 25 different cards in a set. Okay, so I'm looking for that 1. So if I have 24 and I'm choosing 5, okay, that's going to give me what I want. Okay, now where did they get 20 on the bottom? They got 25, choose 5. Where did those numbers come from? There's 25 total cards in the set, and there's 5 total cards in each pack, right? Okay. Okay, and we're only talking about really one pack, right? That's why we're talking about 5, is because we're trying to figure out what's the probability I get a goalie in one pack. Okay, so now when I go ahead and do this, what does this number come out to be? equals 28 total? 0.8. Okay, so I get 0.8. Now, what is that actually the probability of? Is that the probability of getting one? That's the probability of not getting one, right? You guys agree with that? Oh, we're missing the 8 packs. Okay, now, with that, okay, so this is the probability of not getting one out of how many packs? This is 1 pack. Okay, this is 1 pack here because we're doing choose 5. Okay, so this is 1 pack. How many times does this happen? 8, because you buy 8 packs, right? So you need 0.8 times 0.8 times 0.8. How many times? 8 times. So can I just do this? Is that okay? Okay, and that gives me what? 0.168. Okay. So this is the probability of not getting a goalie card out of how many packs? 8 packs of 5 cards each, right? Okay. That's not what we really wanted, though, is it? We wanted the opposite of that. We wanted to know what's the probability I get at least one. Okay, so I don't want this number. I want the complement of that, which gives me 0.832, or 83.2%. That's a pretty good chance, right? Pretty good odds out of 8 packs of cards that you end up with at least 1 goalie card. Probably a pretty good chance you end up with more than 1. Okay. Again, those are the problems where it gets challenging, because it's hard to see. Okay, use this example when you're going through your homework. Okay, I don't want to look at example 4 right now. Okay, let's flip over and talk about dependent events a little bit. Okay, again, we said dependent means it does rely upon something, correct? Okay, so that would be like you guys actually had your problem the other day with the tiles, the Scrabble tiles. Okay, where you pulled one out, right? Does that change the probability of my second draw? Yeah, so those are dependent events, right? Because the second one depends on the first one, and the third one depends on the first and the second one. Okay, so we're actually already doing dependent events. Okay, so if events A and B are dependent, our probability changes a little bit. Okay, your probability of A and B changes to the probability of A times the probability of B such that A already happened. Okay, so that line there in math means such that. So this is read the probability of A times the probability of B such that A already happened. Okay, meaning in that Scrabble scenario, meaning that you had already taken that one A out already, right? So instead of being 100 tiles, there was now how many? 99. Okay, so you got to think, does it matter? Do they depend on each other? Okay, this part is called your conditional probability. You don't necessarily need to know that term. Just know what it means and how to read that, please. Okay. Example 5 and 6 and 7. Okay, we'll glance at those 3 real quick. I'm not going to do a lot of writing for example 5 because they give you a chart there. Okay, but it does tell us that the probability that a listed animal is a reptile. Okay, that's what we want to find. So what is the probability that the listed animal is a reptile? Well, there's 14 reptiles that are endangered, right? And there's 21 reptiles that are threatened. Okay, we just want to know how many reptiles total, or what's the probability of getting reptile. Well, 21 plus 14 is 35. It tells you right there, it shows you the total is 475. Okay, so obviously the probability of being a reptile would be 35 over your total, right? Okay, that's not the challenging part. The challenging part, and actually that's not even bad, okay, the probability that an endangered animal is a reptile. Okay, since they gave it to you, you already know that there's how many endangered reptiles? 14. Okay, now the problem, the only situation you face here is now they're only talking about what? You're endangered. Okay, so you have 14 endangered reptiles, okay, divided by the total number of endangered endangered animals, right? Okay, so just be aware, it's not the total there, right? Okay, just be careful with the wording there. Okay, 6 and 7 are better examples of something like this, so let's take a look at those. On example 5, you just really could have looked at the chart. You probably didn't need any more information, did you? Okay. Comparing dependent and independent events, example 6. Okay, this is a good example. If you randomly choose or select 2 cards from a standard 52 card deck, okay, so we're back to cards, what is the probability that the first card is not a face card and the second card is a face card? Okay, how many cards are there? 52. So I know the first one has 52, right? I want to know the probability that it's not a face card. Well, how many face cards are there? 12. Okay, so how do I figure out what number goes on top? How'd you figure it out? You subtracted it from the total, right? Okay, so the number of cards that are not face cards is 40. Okay, after I draw that card, I want one that is a face card, right? Okay, so do I still have all 12 of my face cards? Yes, because here I'm assuming that this happened. Okay, so now I'm finding the probability of B such that this did happen. Okay, so I'm assuming that I got my non-face card. So I'm going to assume there's still 12 face cards here. But if I took this card out, how many cards are over here? There's only 51 cards now. Okay, that's where it gets a little tricky. It's dependent, but did the top change? We're doing B. Sorry. Because I was just assuming we did not replace it. We're doing B right now. Okay? So when I get this, what do I end up getting for my decimal? 0.181. So about 18.1%. Now that's if I kept the card, right? Now they're wanting to compare if I did not keep the card with that. Okay, so this would be dependent. What if I left them independent? What if I put the card back? It'd be close to the same thing, right? What would be the only thing that changes? This would still be 52. So if you did put the card back, this would be 12 out of 52. Now, which one's independent and which one's dependent? The bottom one's independent because no matter what, there's still going to be 52 cards, right? Nothing's changing. Okay, I'm just drawing one. Okay, that's nice, and put it back. Okay, up here is dependent. Why? Yeah, I have less cards, right? That affects the probability, right? Okay, so if you're keeping something, okay, that's going to be a dependent event. What was this? Okay, so your probability actually decreases if it's independent, right? Okay, the last example I'm going to do for the independent and dependent, okay, is if you're finding 3 dependent events, which is possible, right? With that Scrabble problem, I think we found through G, what is that? A, B, C, D, E, F, 7 dependent events. Okay, shouldn't be an issue now. Okay, it says you and 2 friends go to a restaurant and order a sandwich. The menu has 10 types of sandwiches, and each of you is equally likely to order any type. What is the probability that each of you orders a different type of sandwich? Okay, so let's say it's Mitch, Brody, and Derek over there going to order sandwiches. Okay, yeah, Jimmy John's. Okay, except Jimmy John's decreased their menu. Now they only have 10 sandwiches. That's depressing. Okay, so Mitch has how many choices of sandwiches? 10. Out of 10, right? Okay, so there's a 100% chance that he has a different sandwich from everybody else because nobody else has a sandwich yet. Okay? Brody wants to go, but he doesn't want the same as Mitch. Okay? Now, are there still 10 sandwiches to choose from, though? Yes. Okay, but there's one that Mitch already has. So now there's only going to be 9 ways where they can still have different sandwiches. Okay? And then over here, there's still 10 sandwiches. Okay? But there's only how many ways for Derek to choose and still have not the same? There's only 8 now because these 2 guys already have their sandwiches. Right? So 10 times 9 is 90, times 8 is 720, over 1,000. 72 over 100 is 72%. Pretty good chance that they can go in there and order sandwiches and not get the same one, right? Okay. Personally, I think this lesson's a little bit easier than even the last 2 we've been doing. Hey, but you have to be careful for what? Your independent and dependent, and when you get to your combination stuff. Okay, be careful of that. Okay, I will tell you which ones are going to be your combinations here in a second. Okay. We are adding on to this tomorrow again. Okay, and then, yeah, we'll add on tomorrow. Today's Wednesday. I want to tell you here which ones are combinations if you have some real quick. $26. Oh, sorry, we haven't done all these yet. So let's go through, I don't want to do all these yet, because that example I skipped we haven't done yet. No. Actually, go ahead and do them. We'll talk about the ones that we don't know how to do tomorrow. So your combinations ones are 26, 29. That's it. 26 and 29. You are going to come to a couple problems that you might not know how to do, and that's okay. Okay, we'll talk about those tomorrow. I want to give you guys some work time here, though. I don't want to go too long.